Hello everyone, my name is René Kalbitz. Today I would like to talk about supercapacitors and how to use them in energy storage applications. My aim is to give a short overview over the most important aspects of the design-in of supercaps in energy storage applications. I will cover the classification of supercaps, give a comparison to batteries, say something about the general structure of the layout, and how to proceed at the design-in. I will cover topics like charging, discharging behavior, balancing, lifetime aspects, and the maintain voltage behavior. So I hope I will cover the most important topics that has to be considered. The term supercapacitor is a rather general term. It comprises several technologies. There are the electric double layer capacitors, the EDLC. Their electrodes are usually made of activated carbon or carbon. There are the pseudocapacitors. Their electrodes are made of oxides or conducting polymers which have a high Faraday pseudocapacitance. And there are the so-called hybrid capacitors. Their electrodes use a significant double layer capacitance as well as a pseudocapacitance. Most common type is the EDLC, the electric double layer capacitor. It has the advantage of having no lower voltage, they can be completely discharged, and they have a high power output. Pseudo and hybrids have the benefits of higher operating voltages, usually above 3 volts, around 3.8 volts or so, and thus a higher energy capacity. They have, however, a lower power output, at least usually, and they have a cut-off voltage which must not be undershot. Supercapacitors are available as pouch cells, coin cells, as well as cylindrical cells. The most common one is the cylindrical type, which is shown here in a cross-section view. It consists of a rolled electrode. The electrode consists of activated carbon, which is applied on a metal foil, the so-called current collector, and the electrolyte is completely absorbed by the porous activated carbon. Both the anode and the cathode are then separated by a separator paper, which however does not contribute to any capacitance. It is just there to insulate both electrode sides. Supercapacitors are capacitors, however not used for noise suppression or the smoothing of voltage. Supercapacitors are more like a temporary battery. This charge and discharge characteristic shown here illustrates the difference quite well, I hope. Since the supercapacitor is a capacitor, the voltage increases and decreases linearly if charged or discharged with a constant current. A battery does not. It has more a plateau-like voltage behavior. Consequently, the battery has a higher energy capacity than a supercap. The battery is also able to maintain its charge condition much longer than a supercap can. Supercaps will show a noticeable decay within several days, let's say. On the other side, the charging time for supercaps are much smaller than for batteries. Supercaps can be charged usually in seconds or minutes. The currents for charging and discharging are much higher than for batteries, which make them suitable for short-term, high-power applications. Also, cycle lifetime is much larger than for batteries. The structure of the layout for supercapacitor charge storage units are basically always the same. They consist of a circuit or a unit for charging, a unit responsible for the actual charge storage, the supercap unit, and the discharge unit. The charging unit has the task to provide the necessary charging voltage and current. The supercaps do not require time and voltage control charging like a battery. The charging unit needs, however, to be able to handle capacitive loads and charge the capacitor safely at the desired constant current. All it needs is a current source. The size of the actual supercapacitor stack is governed by the required power and energy. It is, in simple terms, a series and or parallel connection of individual supercaps. The discharge unit has the task to provide the required voltage and current to the load. Usually the powered load or IC needs a constant voltage, which is the supercat not able to provide on its own. So the DC-DC converter or the discharging unit will have to take care of that. So if you want to design a supercap unit, you may in most of the cases follow a certain procedure. First thing you should ask yourself is, what load do I want to drive? How much power at which voltage do I need? And for how long do I want to drive the load? What is the required power in watts? In most of the cases, you will have to utilize, as I already mentioned, a DC-DC converter that provides the required output. If you have chosen the DC-DC converter, you know what input voltage is required. So you know now the required power, and you will know the desired operation time, and you will know the voltage. With the voltage, the operation time and the power, the size of the stack can be calculated, which I am not showing here because it is a bit mathematical and technical. Please have a look at our webpage, or as a customer you may also contact me and I will do the calculations for you. Only so much. The input voltage of your DC-DC converter dictates the size of the series stack. The rated voltage of the supercat is often not sufficient. You often need higher voltages, so you will need a series combination of supercapacitors. From the power and the operation time or discharge time, the capacitance is calculated. With that, the capacitance of each individual supercap can be calculated. Sometimes the required capacitance makes it necessary to parallelize the series connection in order to get the required total energy. But how do the discharge characteristics would look like? So in principle, 3 different discharge regimes exist. As I have said, most people utilize the DC-DC converter, so let's start with that. The discharge regime for a DC-DC converter is at constant power. The corresponding voltage and current characteristics are shown here. The voltage decreases with time and the current increases. Details are given in the references of this talk. Examples for this kind of discharge mode are uninterrupted power supplies or LED driver, for instance. Judging from the requests I receive, this is the most common methods. Most customers that contact me use DC-DC converters. Another discharge regime is the constant resistance discharge. In this regime, the capacitor is discharged over a constant resistance. What you get is a exponential curve everyone knows from the textbook. Actually, I do not have a good practical example, to be honest. I just had one request where a customer wanted to drive a e-motor with a very simple circuitry um, that in that sense represented the resistance. Yeah, please let me know if you have any good examples which I could add to future presentations. The third is the constant current discharge regime. This one is more relevant, let's say, for electrical characterization than for actual applications. Because it's a very simple regime that makes calculation quite easy. Under some conditions, you might be able to apply this as estimation if you use a DC-DC converter. But apart from that, I'm not aware of any good practical examples. Theoretically, a Joule's heating unit could be described like this, but I've never heard of anyone using this practically. So it's more of technical, or it's more relevant for electrical characterization, as I have said. The charging regimes are usually not so much of an issue for the customer, it seems. I don't have too many requests for that, so I will not spend too much time with it. The technical most relevant charging is the constant current charging, which is shown on the right hand side here. That means you have a power supply that can be safely operated at its compliant current, that is to say under short circuit conditions. Most practical applications will utilize this kind of charging. If you have not the benefit of a power supply that can be driven at its compliance and needs to be protected, you would end with a constant voltage charging, which is not as time efficient, and you would have to design in a protective resistors. And once again, the calculations for that are rather technical and mathematical. I would therefore refer to our homepage, or you may also contact me if you need more details. Up to now, we have only talked about general considerations. I would also like to introduce you to a practical example, which we describe in great detail in one of our app notes, which are linked on our homepage. In this example, we have built a supercapacitor unit that is charged by a step-down DC-DC converter at 3 ampere. You can see that here on the right-hand side of the page. It is charged with constant current. If you look at the graphs on the left side, at least most of the time it is charged with constant current. In practice, any constant current charging is accompanied by a constant voltage charging as the capacitor reaches its rated voltage. This is when the difference between the charging state and the charging voltage is quite small. At this point, the current is physically restricted by the ESR. But as you can see at the voltage curve here, we really talk about small voltage differences. The supercap is practically fully charged at this point. The constant power discharge is managed by a boost converter from analog devices, which has an input voltage window of about window of 1 to 4.5 volts. What you see in the graphs is the actual measured voltage and the current, which is red, and the theoretical curve, which is the dashed blue line. As you can see, above 350 seconds or so, the two current curves deviate from each other. The measured power drain is actually larger than the calculated one. This is because the converter becomes less efficient at lower input voltages. The calculations assume, however, a constant power loss, power loss due to the converter, which is of course only an approximation. It shows that it's always good to also make practical examples at the end, and that calculations can only be an approximation at the end. However, all in all, it fits quite well, I think. The actual supercapacitor unit is relatively easy. It is, in this example, a parallel combination of two 50 farad EDLCs, which in total make 100 farads. As pointed out before, in some cases you may need higher voltages, which brings me to my next topic, the series connection of supercapacitors and the balancing. In the following, the balancing is discussed at the example of two series connected capacitors. We also provide an app note about this topic, which is found at our homepage. Please have a look at the references. Any capacitor will have production tolerances of the capacitance and the insulation resistance. In a series connection of supercapacitors, you may have the situation that you have connected two capacitors with two different capacitances. If you then apply voltage, the voltage drop over each capacitor is not equal. The capacitor with a lower capacitance will see a larger voltage than the one with a higher capacitance. Thus, you may risk overvoltage. To prevent that, you should employ a balancing. The most cost inexpensive and technically simple balancing is the balancing with resistors. As you can see in the circuit on top, please do not get confused with the arrows. They indicate the flow of current. As I have already mentioned, if you are interested, please have a look at the corresponding app note. In this example, we have chosen intentionally two different capacitors, a 10 farad and a 15 farad capacitor. The blue voltage curve is for the 10 farad and the green curve is for the 15 farad capacitor. Purple is the total voltage, and the red curve is the difference between the two capacitor voltages. As you can see, we start with a large voltage difference where the 10 farad is charged over 3 volt. This discrepancy is then balanced over time of about 600 minutes. It is the slowest balancing and more a balancing for the internal resistance than for the capacitance. Faster, but still not expensive, is the balancing with diodes. It is about a factor of 10 faster than the balancing with resistors. And they prevent reverse voltage. So it's a solid strategy. Even faster is the balancing with MOSFETs and the active balancing with a balancing board, which is shown on this slide. Balancing with the balancing board is practically the balancing with a DC-DC converter. Actually, the balancing board, which is shown in the lower part of the slide, is the only one that is balancing fast enough to prevent overvoltage right from the beginning. Supercapacitor balancing is at the end a weighing of interest. You have to decide what is most important for you. Is it pricing, the energy dissipative behavior? Is it the balancing speed? You have to make up your mind as a developer. As you see in the table, there is not one technology that is best in all categories. In my mind, the Zener diet is maybe a good compromise. If you use, however, the balancing board, you have a carefree solution. The evaluation board utilizes the buck-both supercapacitor charger and the balancer from analog devices, and it's a carefree solution. So you have to make up your mind. Another important aspect to consider is the lifetime. For supercapacitors, it might not be suitable to think in terms of lifetime, but in terms of capacitance degradation. Since you may have certain tolerances for your required energy capacity, you may also have the opportunity of oversizing your layout to compensate for certain degradation. In the left graphic, you see the relative decay in capacitance after 2 years, depending on the temperature and the voltage. The degradation is in percentage and color-coded. If you may only allow for 20% degradation, then you should stay within the orange area. For example, if you want to drive the EDLC permanently at 2.7 volts, the operating temperature should not be above 35 degrees. Our model, which we use to calculate these graphs, also allows the prediction or estimation of degradation for certain mission profiles, as you can see on the right hand side. The plot here on the right hand side, in this example we have assumed a operation temperature of 50 degrees Celsius and a permanent voltage of 2.1 volts. As you can see, you are pretty okay until 5 years or so. After that, the degradation is quite strong, and you might even not be able to cover that with an oversizing at the very beginning. So if you plan your layout, you also have to consider what is the operating environment. So what to learn from is you may compensate for degradation by oversizing. However, the supercapacitor is not the best solution for very hot environments. This is very clear. Last but not least, let me mention the topic of self-discharge or maintain voltage. The self-discharge is driven by the leakage current, which is given in the data sheet. Usually it is in the order of microampere, but most people don't find that always helpful. You certainly need it if you develop your balancing strategy, but very often people don't know what to do with it. A bit more practical is the maintain voltage value, I think. At this kind of measurement here, the capacitor is charged from a certain amount for a certain amount of time and then disconnected from the voltage. And the voltage is measured then. The result for a 100 farad EDLC is given here in this graph. It was measured under different pre-poling times and operation temperatures. As you can see, the maintained voltage behavior improves with the length of the poling time and decreases with increasing temperature. As you can see, the supercap can hold usable voltages up to several days. However, it could not be applied in applications like smoke detectors, for instance, which have to last for years. For that, a battery is more appropriate. I have mentioned that, I guess, at the beginning of the talk. In summary, what is it that you should take home? Supercapacitors are high power energy storage devices. Concerning the procedure of the design in, the discharging is very often under constant power. The charging usually is under constant current. For the balancing, I recommend always the Zener diode. Concerning the lifetime, the supercaps are best at the mid-temperature regime, let's say below 50 degrees Celsius, if they have to last for, let's say, a couple of years. And concerning the maintained voltage, it is clear that they are good for short-term energy storage in the order of days or so, but not several weeks or even years. If you have any further questions, I will be happy to answer them. Please contact us under the given email. You may also give me a telephone call if you like, and more details are also found at our homepage, where you also find all the keynotes which I have mentioned throughout the talk. Alright, this is it from my side. I thank you very much. I hope you enjoyed the talk and have a good day.